All right, let's get right into it. For a long time, AI was really about generation, creating text, making pictures, but the game has totally changed. We are now in the era of AI reasoning. And these new, quote-unquote, thinking models have hit a computational wall. The old systems just can't keep up. So today, we're going to break down Google's answer, a totally new blueprint for AI infrastructure they're calling Ironwood. And this slide right here, it just nails the problem. On the left, you've got the old way. AI was linear, it was predictable. You put something in, it processes, you get something out. Simple. But look at the right. These new reasoning models are recursive. They run these complex loops of logic that create insane memory pressure and huge latency bottlenecks. It's a fundamentally different problem, and it demands a fundamentally different kind of machine. So, let's start where it all begins, at the very heart of this new machine, the Ironwood chip itself. Now, this is a big deal. It's Google's first ever dual compute die TPU. See, in chip manufacturing, there's a hard physical limit to how big you can make a single piece of silicon. It's called the reticle limit. Well, Ironwood basically shatters that limit by putting two incredibly powerful compute dies into one package. This move alone doubles the compute density and gives it a jaw-dropping 10x performance jump over the last generation. And the specs on a single one of these chips are, well, they're just staggering. Over 4,600 T-flops, that's trillions of calculations every second. But here's what really gets me, the memory. 192 gigabytes of the latest HBM3E memory, delivering a mind-blowing 7.3 terabytes per second of bandwidth. That is the fire hose of data you absolutely need to feed these new thinking models. And that 1.2 terabytes per second of I/O, that's the secret sauce for scaling this whole thing up without creating traffic jams. I love this slide because it shows so clearly how the chip actually gets its work done. It's not just one big engine. You have the tensor core, which they call the industrial press. And yeah, it does all the heavy lifting, the big math. But the real game changer is that 4th-gen SparseCore, the prep chef. It handles all the other tasks, the embeddings, the collectives, and it does it all in parallel. What does that mean? It means the big industrial press is never sitting around waiting for work. It's a massive win for efficiency, all fed by that ultra-fast warehouse of HBM3E memory. Okay, so we have this unbelievably powerful chip. But a single chip, that's not a supercomputer, right? The real question is, how do you get thousands of them working together as one? Well, let's see how Google assembles this giant. So this diagram here, this unbroken architecture of scale, is basically our map. The first step up from the chip is the tray. This is the foundation, holding 4 of those Ironwood chips. Now, you can probably imagine putting 4 of these little powerhouses that close together creates an absolutely immense heat problem. And here is the seriously elegant solution. This is Google's 3rd-gen liquid cooling system, and they've got over 8 years of experience with this stuff. Now, the key innovation here is the parallel water flow. See, in older designs, the water would go past chip 1, then chip 2, and by the time it got to the last chip, the water was already warm. Here, all 4 chips get a fresh, cool supply of water at the exact same time. This is crucial. It means every single chip can run at its absolute peak performance. No one gets left behind. Okay, back to our map. We've solved the heat problem at the tray level. The next step is to combine a bunch of trays into a single rack. And now the challenge shifts from managing heat to moving just unbelievable amounts of data. And the way the rack is designed is just plain smart. For all the super fast, short-distance chatter inside the rack, it uses good old copper interconnects. They're cheap, they're reliable, they get the job done. But for connecting to other racks, where you need massive bandwidth over longer distances, it switches to high-speed optical links, shooting light out of those 18 high-density ports. It's a hybrid approach that gives you the best of both worlds, cost-effectiveness and insane performance. All right, we've gone from the chip to the tray to the rack. Now you need to get ready for the final and frankly the most impressive part of this whole architecture. 9,216. Just let that number sink in for a second. That's how many of these incredibly powerful dual die chips are about to become one single massive supercomputer. And this is the final form, the superpod. The absolute magic that ties all 9,216 chips together is something called an optical circuit switch, or OCS. Think of it like a telephone switchboard, but for light. It can dynamically connect any chip to any other chip, turning them all into one giant machine. This also lets you digitally slice up the supercomputer for different jobs.
And this is huge. If one part fails, it creates a tiny blast radius, isolating the problem without taking the whole system offline.
So what we're looking at here is more than just hardware. It's a completely different philosophy. With OCS, you're getting away from the old model of thousands of little computers sending messages back and forth. It's less like a city of houses yelling at each other, and more like one giant building where everyone shares the same library. There's no copying data. Every single chip can natively access the entire memory pool. It's a true shared memory system at a scale nobody's ever seen before. And the result of that new philosophy? A world record. 1.77 petabytes of shared HBM memory. This is the absolute holy grail for running today's gigantic AI models. You can fit the entire thing in this one unified space, which completely eliminates the bottlenecks from moving data around. So let's just pause and look at the final stats for one full superpod. 42.5 exaflops of compute. That record-breaking 1.77 petabytes of shared memory. All 9,216 chips wired together with light. And maybe most impressively, it does all this with twice the performance per watt of the last generation. This isn't just an improvement, it's a whole new class of machine. Now look, building a machine with that much raw power is one thing, but actually running it reliably and efficiently without, taking down the entire power grid, that is a whole other beast of a problem. On the left, you see the hidden danger. Big AI training jobs can cause these massive, millisecond-long power spikes. We're talking megawatts that trip circuit breakers. Now, the power comes back instantly, but restarting the software job takes minutes, and that just kills your efficiency. So, on the right, you have the solution, Project Smoothie. It's a full system of hardware and software that actually predicts and smooths out the power curve, unlocking up to 30% more work from the exact same power budget. It's brilliant. And, of course, a machine this powerful is completely useless if it's not reliable. A single bit flipping randomly could derail a training run that's been going for a week. That's why Ironwood has this multi-layered shield of what's called RAS, reliability, availability, and serviceability. It has features to stop silent data corruption. It can even repair hardware logic while it's running. And for security, there's an integrated root of trust, which enables things like secure boot and confidential computing to protect both the model and the data. So when you put all of these pieces together, the dual-die chip, the cooling, the optical switches, the power management, what does it all really mean for the future of AI? Here's the most important takeaway. Ironwood is not just another incremental hardware upgrade. It's a fundamental architectural shift. The whole design philosophy, this idea of unbroken scale-up and totally unified memory, this is the foundation that's going to enable the next era of computing, the zettaflop era. And this isn't some science fiction concept. These systems are being deployed right now at hyperscale, and they'll be available soon on Google Cloud. So, as we've seen, Ironwood is way more than just a faster chip. It's a new paradigm for computation, one that was designed from the ground up to solve the specific bottlenecks of modern reasoning AI. You could say it's a machine that's actually built to think. And that leaves us with one final, really exciting question. What will humanity build with it?